Okay. So how's everybody doing? Happy this is the last class, or some of you are graduating, right? Or is anybody graduating? Just one. Okay. Uh, so I guess this class and the exam week stands between your summer. Uh, uh, okay. So what I'll try to do is today's lecture will be a little bit short, hopefully, and then we can just go over some of the things that we did after the midterm as well as the whole course. Okay. So today we will look at, last time we looked at Q-learning as an algorithm. So even if you did not understand some of the details, we'll actually revisit some of the approximations that we're doing from the Bellman optimality equation. So we'll just revisit that. It's just an interpreted, it's just I guess a intuition-driven understanding of Q-learning. It's actually a formally, we can also understand Q-learning, but we're not going to discuss that here. So that's what we're going to do. So Q-learning with function approximation, and that should ring a bell. Function approximation, anytime you have a function approximation, you can think of linear functions, nonlinear functions, and so we'll use actually neural networks, and which means we'll use, in fact, we'll use convolutional neural networks for at least the Atari game playing demos that we saw last time. Okay, and so that's the second point. So this is called deep Q network. So the deep Q part is actually the function approximation is a neural network. The third goal would be to just understand how to, there's a how to solve certain other type of decision problems. Like for example, in games like Go, you make a move, the opponent makes another move, you make another move. So in that situation, there's this nice algorithm called Monte Carlo tree search, which lets you explore that space of possibilities in a nice way. So we'll understand a little bit of details on that. And then the last goal is to round up. Okay, so basically we have come full circle. So since we were talking about graphical models, okay, we've not looked at deep learning, right? We went into structured data sets essentially, or things are random variables, okay, and then relationships between them. That's what we did in graphical models. Then we moved into A/B testing and variations, which include multi-armed bandits, contextual bandits, and then last lecture we saw basics of reinforcement learning, a way to, and it's just language to describe what's happening. How do I learn? Should I learn the model of the environment or model of the world, or should I directly optimize for things like valuing certain states, or valuing in being in a certain state and taking some action? Okay, so these are all concepts that we saw last time: value functions, policies, and modeling the environment, and we'll revisit them. And so the full circle here is that here today we're going to look at use of neural networks in certain decision making problems. So point 2 and 3, the second one is using a convolutional neural network, and point 3 is using a regular. It may also be using convolutional neural networks. So we'll see when we get there. Okay. To solve two very example problems, both in game domains, but you can imagine you can extend this to other domains, like, generally engineering as well as business analytics domains. Okay. So that's the goals. Also, is anybody confused about the exam time? It's on Wednesday evenings. So previously it was showing on the UIC calendar as a slightly different date. But if you're not confused, then don't worry. But people are confused, go back to the UIC's exam schedule and see when the exam is. It reflects exactly what is there in the syllabus. It's next Wednesday, same time. Okay. Let's see. Okay, so let's start. So today's lecture, we're going to first start with approximating value functions, because that's the type of function that we saw last time when we introduced it in the context of first the Markov reward process and then the MDP. and then we also discussed how it's relevant in a reinforcement learning algorithm. Basically, Q learning is all about kind of learning the Q values, which are just state action value functions. Okay, and then we'll look at two case studies essentially. One is DQ network, and the second one is AlphaGo from 2016. There are improvements since then. There is AlphaZero, AlphaGo 0, and so on. But we'll look at the original version. It's just a flavor of what are the main ingredients in such methods, okay, or such solutions. So yeah. So let's recall what the Q learning algorithm was, and before that, I'll just repeat what Bellman optimality equation is. Okay, so Bellman optimality equation is this equation here. Okay. So remember, Q was the expectation over the rewards that you can get, okay, or from T1, T plus 1, T plus 2, T plus 3 onwards. If I start from a given state S, okay, at time t, and take an action A at time t, and follow a particular policy, okay, that was Q pi of S comma A. Okay, so Q star of S comma A is the best among all the pi's which can maximize this Q values, okay, for all state and action pairs. Okay, and it turns out that the Q star of S comma A satisfies an equality. Oh, it's not. I didn't realize this. Yeah, so Q star S comma A satisfies this equality constraint or equation. This is called the Bellman optimality equation. Okay, so it relates few things, right? It relates Q star of S comma A with other entries. So think of Q of S comma as a matrix, right? Last time we said you can have at a given state for a given action a number. Okay, so you can have it for various states and various actions. Okay, so that was the tabular representation of the Q function. Okay, so if you have 10 states and 3 actions in each state, then it's a 10 cross 3 matrix. For simplicity, even before getting into value function approximation stuff. So Q star of S comma A is the best, is one of the best entries of these, one of the best matrices that you can have, and that matrix best in terms of a particular objective, right? Maximize the long-term rewards. Okay, so that was the objective. So there is a policy corresponding to this, which is just the argmax of Q. If you are in a state S, the action that you should take is just the argmax. So if there are 3 actions in a given state, then there will be 3 numbers: Q star of S comma action 1, S comma action 2, S comma action 3. Then pick the number which is the highest. Okay, that's a simple policy. So that policy is the policy that you care about. Okay, that's the best policy. Okay, best in terms of maximizing the expected total reward. Remember, the first goal in reinforcement learning is to maximize the expected total reward, because there's dependence on states that appear in sequence. There's a temporal aspect of this problem which was not there in bandits or A/B testing or contextual bandits. Okay, so you're not myopic. If you're myopic, then you take a greedy action in a given state, but you care about taking an action now with the objective of being long-term profitable. Okay, so that's the important thing. And Q, the state action value function as well as state value function, capture that long-term aspect. Okay, and so let's say this matrix is known, Q star is known, then Q star satisfies this equation, and that's the Bellman optimality equation. Okay, so basically it relates one entry of the matrix to several other entries of the matrix. Okay, that's all. And for this, you need to know the reward that you can get, expected reward that you can get in the given state and a given action, as well as the transition probability, I guess, matrix. Okay, so this is like if you are in a given state and a given action, what's the probability that you'll go to some other generic state S prime? Okay, and so you're summing over all the generic states S prime and all the Q values in that state. Okay, and so this is called the Bellman optimality equation, which Q star satisfies. Okay, and this diagram here is just representing so that you are at a situation where you've taken a state, you are in a state and you're taking an action A, and then you will randomly potentially get to some other state S prime, and in the S prime state you can take yeah, you are supposed to take the best action. That's this arc, I guess, diagrammatically speaking, and that best action. So that number q star of s prime comma a prime is related to q star of s comma a. Okay, that's it. So it's just an interpretation of. It's just a nice set of conditions which talk about that q star satisfies. Okay. Now, why do we care about this? Is this equation is the basis for solving for optimal policies in Markov decision processes. If you know the dynamics, which is this p s prime a, and if you know the rewards r of s comma a, so somebody tells you this conditional probabilities and the r's, okay, some objects basically, or matrices or vectors, then you can compute the solution q star by just solving this equation. So there will be one equation per s comma a pair. So maybe if there are 10 states and 3 actions, as I was saying, then there will be 30 such equations, system of linear equations actually non-linear equations because there's a max operation there, but system of equations, and then you can just solve it. Okay, try to find numbers such that they fit that equation. Okay. So that's good. So that's the basis for algorithms when you know the dynamics. If you don't know the dynamics, still you can kind of reason from here how you get to an algorithm like Q-learning. Okay. So for that we do two things, right? Yeah. For that we need to deal with two things. One is we don't have this dynamics, which is the p of s prime a, and we also don't know q star itself, right? I mean, that's what we want to find. So to deal with this, we do sampling. Okay, so we'll sample and get to next state. Okay, sampling just means access to simulator or try out something. The simulator, I don't know how complicated it is, or if it's the real world, that will tell me what the feedback is. So I don't need to have maintain a transition probability matrix or anything like that. And there's something else that you need to do, which is not in this equation, which is you need to explore. Okay, so exploration was a concept that you saw in even in multi-armed banners, right? You were supposed to do greedy, epsilon greedy was a good idea because you would be maximizing profits from the information that you know so far, but also you want to figure out if there's something that you don't know much about, but maybe you try it and you figure out that that's better. Okay. And the incremental iterative update part is actually something that you can do even if you know the dynamics. Okay, so this is well an optimality equation here, the star. This can be converted to what is called algorithm, which is called value iteration or Q value iteration. If you have an equation like this, so if you have an equation, how do you convert an iterative algorithm? You start with left hand side, put some random values, and evaluate the right hand side for all the state action pairs. Then take those as the values on the left hand side, compute the right hand side, update it. Okay, so that's the iterative algorithm. So whenever you have so f of x is equal to x, let's say, so so left hand side is like something like x, which is unknown, and the left hand side is f of x, some arbitrary complicated function of x. Then you start with x naught, plug it into f of x naught. Okay, and that will evaluate to some x1, plug that back into f of x1, f to get f x1, f of x1, and so on. Is that clear? How to make it iterative? Okay. So sampling is just demonstrated here. Okay, let me just put this as equality here. So because we don't know the transition probability dynamics, so we're just gonna get to some next state by just asking, just trying out an action A right now, trying out this action A, get to some specific state S prime, and we know the Q value there, but that's not enough because this is going to correspond to Bellman expectation equation. So what we do is change this underlined Q to a max operation. So instead of so what is this action A prime here? It's going to be the best action that you can from that state S prime. Okay, so what I'm trying to say is that this Q is going to be replaced with a max over A prime of Q of S prime comma A prime. So I'm not really going to look at so I'm in a state S, I took an action A, I went to some state S prime. I'm not going to again sample an action there. At that state, I'll look at all the Q values that are possible. Let's say 3 actions, then the 3 Q values there. I'll take the max, and that's what I've substituted here. So what's missing here is that P. Okay, there used to be a sum before. after gamma there used to be sum of the dynamics. We removed the dynamics. That's the sampling part. Okay, and yeah, and the iterative part is that if I have previous values, I can compute the right hand side and update the Q values on the left hand side and keep repeating this in a loop. Okay, is that clear? And this second point about exploration is that if you do this, so that's fine. So if you do this equation is not telling you what action you are supposed to take in the next round. Okay, you can be greedy. So at any given point of time, you have this Q matrix, right? States cross actions, 30 entries, or 10 cross 3 matrix. At any given point of time, you can always be greedy, right? If you're in a certain state, you can just look at the 3 numbers and pick one of the actions. Okay, so that's greedy. But as you saw in Q learning, you're supposed to like explore a little bit because otherwise you will not be able to get to the right Q star. Okay, I mean, so this iterative algorithm with some exploration actually gets to Q star was the statement that we made, which is I guess this one. Okay, and so what is the algorithm? The recap. It's going to be that initialize. So think of a matrix that I'm maintaining, maybe all zeros. Okay, let's say it's 10 cross 3. And you start from some starting state, okay, starting state, and for every round you take an action arbitrarily, which is explore with some probability 10%, and with 90% probability you exploit, which is take the argmax of the Q values at the current state. Okay, maybe if the same number you can break ties arbitrarily, that's fine, and then you update it according to the equation that we saw before. So Q, the left hand side is right hand side plus some. So the right hand side is nothing but 1 minus alpha times the previous value plus alpha times some new value, which is r plus gamma, this max term. Okay, that's the same thing. So I just took, there's Q in the first term and the second term. I just took it common. It's 1 minus alpha times the previous value plus alpha times the new value. Okay. Now this underlying thing is called temporal difference error, and epsilon is the exploration parameter. Remember, we did it in MAB multi-arm bandits as well. Epsilon is an exploration parameter. Alpha is also called learning rate. It's, I guess, overused term. It's here we are learning the Q star, hopefully, eventually. So that's why this is a learning rate. And under some assumptions, people have shown a long time ago that this gets to Q star. Okay. These assumptions are more technical, I guess, more mathematical curiosity. But you can, in practice, you can run this algorithm on any toy setting, like a maze solving problem. Maze examples we saw last lecture when we talked about what is a value function, what's a policy. So such examples where you have to, like a mouse has to just try different things and figure out how to get from a starting point to a goal. Those types of things you can have as essentially a function or a Python package, and you interact with it and get to Q star, which is the optimal thing that you should do in that maze. Okay. But so today's topic is actually, so I just recapped Q learning, but today's topic is about trying to bring in deep learning into the picture by saying that if you have a grid, let's say this is the maze, okay, and you are at, so the green point is the starting point for you. So here, over here. And you need to get to the end of the, maybe this is the door over here to get to the next level. Okay. If you have this 2D representation, then you have xy coordinates, right? Given x comma y pair, 2 numbers. If I do a move left, right, up, down, forward, backward, left, right, then I'll go to some other grid point, which is again 2 numbers. Okay. So if somebody tells you the state representation has 2 numbers, then you can update the state based on what you did. Okay. But what happens in the real world is, you may not be able to represent the state nicely as a bunch of numbers. I mean, as a bunch of like really succinct numbers. So if you take the same grid world, or this grid type of a environment or the world into its 3D counterpart, which is shown as a screenshot here, then and let's say you only have a camera, so you can't measure your position, okay, as an xy coordinate. Then that's the input, that's the feed that you see every second or every 10 seconds. Then given that feed, it's not clear how you can do the stable version that I talked about. So Q learning so far we have talked about is roughly maintaining a table at any given state. you're supposed to maintain the number of numbers, which is the number of actions possible in that state. So let's say it's the same number of actions in every state. Then if there are 10 states, each state has three actions, so you maintain a 10 cross 3 matrix, right? But in this, if this is a state, okay, let's say it's an image, it's whatever pixel cross pixels, x pixels cross y pixels cross some color RGB, then there are too many numbers, right? And that's also, it's not clear whether that's the you can enumerate them, as in you cannot maintain a table with all images that is possible in an environment. Okay, maybe for really small environments like this, it's still possible when the camera is slightly moving, but in real world you can't really enumerate the states. Okay, even though there are only 4 actions, at least are just limited in number. So the way to get around this issue of states being too many in real world, okay, especially camera-based inputs, or in this class we've been looking at unstructured data, so camera, text, images, or text-based inputs. Then you would want to have approximation. So an approximation of the Q table. So Q, or in general, so a 2-argument function is like a table. So in this case, we're going to approximate this function. Okay, we were initially thinking of it as a table. Now we're going to think of it as a general function, which takes arguments, state, and action. Okay, and state can be a rich object like an image. Okay, so this is what we'll discuss for majority of the class, but you can actually do function approximation for the other value functions. So for example, you can also do function approximation for V of s. Remember, V of s was just the expected value, expected total reward from a given state following a particular policy pi, okay, from that state onwards. So in that state's action itself is also pi of s. You apply pi, the policy, on the current state to get to the action, whereas Q was slightly different. It was saying that in the current state, take an arbitrary, the action that I choose, which is the second argument, and then apply pi later on. Okay, so that's the difference between these two. And you can also approximate policy. So pi of s itself is a mapping from state, which could be an image, to a joystick move, forward, left, right, or something like that. And so that itself could be a function, right? So it could be from an image to some discrete numbers is essentially what like a classifier would do. Okay, so this can be a deep network, as this can be a neural network or something like that. And you can approximate the model also. The model means the reward function and the transition probability matrix. Okay, and once you can do that approximation, then there are some challenges which come up, because if it was the Q-learning update, remember Q-learning update was saying that, if I'm in a given state, let's say some image, and take a certain action, forward, left, right, then I need to update a number corresponding to that state and action. Okay, but if you have a function like a neural network or something else, it's not clear how to, we're not, if it's a neural network, there will be parameters that need to be updated. We cannot update the function's evaluation directly. So there's some non-triviality there. Okay, because of a function approximation. Okay, so the vanilla Q-learning update has to be slightly modified, is what I'm trying to say. And if the function is differentiable, some functions are not differentiable, but neural networks for us, in our case, have been differentiable. That's why we've been using backprop and all that stuff. So then it's good. Then you can just then you can use the usual gradient descent type of techniques to update. So we'll see that in the next few minutes of how to update. Okay. So let's dwell a little bit on Q function approximation. So instead of storing the state cross action matrix, we're going to represent the function approximator as something which approximates some Q. So let's say Q star. Okay. So I'm switching between lowercase, uppercase, but it's same Q state action value function. Okay. So now, because it's an approximation, it will have its parameter. Okay. It will have its parameter W, and there are two I guess ways to think about this approximation, and this is just for semantic reasons. In one version, you have both state and action as the input, and output is just the Q value at that state and action pair. And the second version is state is the only input, and then you're outputting the Q values for all the actions that you can potentially take. So what's the difference between the first and the second diagram here is that you stack a bunch of first diagrams, like whatever, if there are 3 actions, 3 such first left-hand side blocks would correspond to the right-hand side picture. Okay. So in this case, there are let's say 3 actions, and you need to output 3 numbers, and you concatenate 3 function evaluations. Okay. So anyway, this is just a block diagram representation of a function evaluator, where you're trying to now say that function approximation, where you're now trying to say, I don't want to update the entries of q value itself, I want to update this parameter. Okay, so I'm switching from updating the q values itself to updating the parameter. And there are many functions, as you have seen in previous classes as well as this class: decision trees, linear models, neural networks, nearest neighbor approximations, and so on. And so let's actually look at how do we approximate the q function. So okay, so let's say now let's step back from reinforcement learning and just talk about, okay, let's say somebody gave me the true q function, okay, q pi of s comma a. I want to approximate it with q hat of s comma a comma w, where w is the parameter of this approximator, right? So so I want to approximate this guy, which let's say I have access to, I can evaluate it with a approximating function q hat. Okay, then one way to approximate it is to take the difference between what is my target minus the function that I care about, and write it as a function of, and take, let's say, squared loss, squared loss difference or squared error difference between these two guys. And so that depends on the w parameter I chose for my approximator, so optimize for the best w parameter, okay, which minimizes this error. Okay, so why this expectation? So you can just naively just think of this as sum over s comma a pairs. Okay, so you want to have a good approximation all over the place for every state action together, all the state actions together. So that's why there's some expectation operation here. And also, so q values are supposed to represent long-term rewards. So there is, for a given policy, so you care about the dynamics that are there in the system. Okay. So anyway, don't worry about that expectation. So you have the usual squared loss function. So if you take the first derivative with respect to squared loss and multiply with minus 1/2. Okay. So why minus is because my function is on the right hand side, so it has a preceding minus sign. So there's if you take a derivative, you get a minus sign in the front. 1/2 because if there's a square, then there's take the derivative, then you get 2x, like square, derivative of x square is 2x, so the 2 and 1/2 cancels. So ultimately what we get is a term which looks like this, right? So the term inside the square loss, like target minus my approximator times the gradient of the approximating function with respect to w. Okay, so this is a simple derivative of the objective function in our case. This is j of w, and then given this objective function, we can just update our weights by saying w t plus 1 is wt minus the gradient, which is, so minus alpha. Okay, I don't want to write alpha. So gamma times the gradient of w with respect to j of w, right? The usual loss function, gradient of the loss function, negative gradient, update the w's. Okay, so that's what's written here. Delta w is just the difference between current, new w minus old w, and it's equal to learning rate times the thing in the previous equation. Same thing with alpha in the front. Yeah, I wrote gamma here, but you can just change it to alpha here. Same thing. There's a 1/2 here, just to make the equation the same. Any questions about this? So this is how this is just, yeah.
So how do we get the q pi of s comma a? Is it like?
So for now, and just for hypothetical purposes, we are just saying if we had q pi of s comma a as a target, then, and if you want to approximate that function, then this is how you would approximate. Let's say I gave you, let's say the function is 3x squared plus 2x plus 5. Then and I ask you, and I ask you to approximate, let's say, linear function, okay, which is alpha 1x plus alpha 2. Then you have to figure out alpha 1 and alpha 2, or let's say w1x plus w2. Then you want to figure out w1 and w2. Even if I told you the function, you need to still figure it out, right? So you would do this type of a gradient update. This is not the only way, but this is one way to find the best w1 and w2. Yeah. So here's so let's say so what I'm going to do next is actually specialize the q of s comma. So this guy, I'm going to make it a linear function, just for the thought experiment to kind of ground the facts. So let's say to make it a linear function, I need features. Okay, so if to make q hat of s comma a, I want to make it a linear function, then there has to be something like w transpose x, right? Something like this. So what is that? What is this x? X has now depend on s comma a. Okay, so it's like a feature extractor. So if from state and action pair, I can compute some features, maybe little n number of them, and if I can get these, if I already have feature engineered and I have this n-dimensional feature vector for a given state action pair, then my approximation would be just a linear function, right? X transpose w. Okay, this is a linear function, and then the gradient update. So the gradient of the term underlined, which we saw here, which is what is needed over here, right? This is the gradient of the function itself, would be the feature vector at s comma a, right? So gradient of the function at a given w is the feature vector itself. Okay, and therefore the update is going to be just alpha times the difference between, which is the error, times the feature vector. So is this clear? So the feature vector is n-dimensional, w is going to be n-dimensional, and so it's an n-dimensional vector update. Okay, we have seen this in the first lecture. Okay, any questions about this part? Okay, so now what we're going to do is we don't know the q pi of s comma a, so we'll kind of move towards understanding how we can update when we don't know the q of s comma a. Okay, so we'll drop the pi here because in q learning we are trying to keep changing pi. So implicitly there is some policy which is being changed, okay, when we update the q values, because remember once you have q values, there's a policy corresponding to it by taking just the argmax over actions for any given state. Okay, so and as update q values, I have different pi's. So okay, that's the relationship. And so this is the q learning update. Remember, so q is just the previous q plus alpha times the temporal difference error. Okay, I don't know, e r o r. So okay, so at optimality just means that if remember we made this update equation by saying we didn't have the dynamics, right? We didn't have the dynamics, and we said we don't know how to make the left hand side equal to right hand side. But at the end, q star or the Bellman optimality equation says left hand side is exactly equal to right hand side. So which means that this should be equal to this, right? So remember, just if you substitute q star, the second term here is the left hand side and the first term there is the right hand side with an expectation operator. This expectation is capturing that p script p transition probability kernel. Okay, so what I'm saying is you do q learning update. Ultimately, if you keep updating the q numbers, ultimately you get q star. That q star has to satisfy Bellman equation, right? So Bellman equation written in a different way is just this. Okay, it's just pushing the left hand side to the right hand side. So it's just saying that the right hand side minus left hand side is equal to 0. Okay, there is nothing else happening here. So at optimality, as in like if q learning converges to some q star, then this should be true. So why not just use this as our objective, which means that why not make an error loss function which is going to be this term minus this term, where these guys are what we're going to approximate using the parametric form q of s comma a comma w. Okay, so we're going to just change the q to to include the third thing, which is the third argument, which is the parameter, and those w's are what I'm going to adjust to minimize the difference. Minimize the difference between these two terms. Okay, minimize the difference between these two terms. Okay. And that's essentially, okay, this I'll get to soon. Okay. Oh yeah, actually we, at this point we're gonna, so we'll get into the details of this step pretty soon, in the sense of how are we gonna minimize these two differences. So the difference between this and what we saw in the previous slide is here we knew q, this thing in the box, blue box, we assume that we know q of pi, and we're just asking how do I get an approximator. Okay, this is like nothing to do with reinforcement learning. It's just a function fitting exercise. I have already told you what the target function is. I'm asking what is the best function you can come up with, and you just minimize, let's say, square laws, and you'll get this. Whereas in q learning, we care about somehow getting a q value which evaluates, which eventually hopefully gives me an equation like this, that q value satisfies this equation. Okay, to get there, we are saying we should incrementally minimize. The difference between the first term and the second term. Okay, and we'll get into some details of how we do that in the context of deeper networks in a couple of slides. Okay, so we're going to take a segue now to talk about modulo that issue of how do we minimize the difference between the two terms, target one term and the other term, even though the w is involved there. People have done it, okay, in several years ago, 6 years ago. Some folks were able to create methods that could, the q learning thing with that minimizing the difference between the target and the left hand side and the right hand side. And they use deep neural networks to get to really good playing performance on these games. Okay, and so what is the okay? Let me just okay. So issues with function approximation we'll talk about later. Okay, I think it's a misplaced slide there. Any questions so far? So we just now have to figure out how to use that idea that we saw if we know q of pi to the situation where we don't know q of pi inside the q learning loop. Okay, but its q's are parametric. Okay, that's the only thing we need to look at, and we'll look at it in terms of actually a case study, which is actually the slide which we saw before, which is the DQ network. Okay, deep Q network that was used to solve the Atari learning environment. So, which is this. We'll understand how to do that in the context of the DQN. Okay. Any questions so far? Okay. So before I get there, so why deep learning? We have actually seen this several times. I think maybe 6 lectures we kind of drill down to why not deep learning, right? So here's a picture of like what people used to do before SVMs, images to handcrafted features, and then maybe the last level would be once you have handcrafted features, use an SVM classifier or things of that nature. And we saw since about 2012, people have been looking at really these deep neural network architectures as the predominant way of doing classification and recognition. Okay, although these methods were there for a long time, both types of functions. Okay, and recall that CNN is also an example function approximator. And the reason why I'm flashing this slide here is that we'll use a CNN when we talk about DQN. Okay, so our function approximator with the W there is actually the parameters of the feature, of the the filters, of the CNN. Okay, filters and the fully connected layers of a CNN. Okay, so what does CNN do? One thing is it does weight sharing, so you actually have a lot of reduction in weights in at least the initial few layers. And second thing is it does, of course, does pooling, but the thing it's trying to capitalize with respect to the type of data that it looks at, which is images or sentence, is some locality, some sort of a translational invariance where there are features which are like low level, and then they kind of build up in a hierarchical way to higher level features. Okay, so this is something that we have dealt with in quite detail. So I just explained at a very high level, right? So let's get to DQN. So what's the DQN architecture? So this is I'm just trying to repeat what the Q learning problem could be in this games domain. So you would have an observation, which would be the screen of the game. Okay, the screenshot of what's the situation of the game, like all the pixels. You make that observation, and this is a block we need to create, which takes an action, joystick action A, and that's fed back to the simulator. Okay, so there's a simulator which just given or the environment which given an action in the current screen tells me what's the next screen. Okay, and as well as updates the score if I gain something, right? So DQN uses Q learning with a function approximation, And in fact, the function approximation is a CNN. And in addition to, so we'll see that while we are modifying that Q-learning update, remember we wanted to, once we introduce W, it's not clear how to do the Q-learning update. We'll look at some tweaks to get to that get to an appropriate Q-learning update. So through this example of DQN, okay, and it'll require it'll kind of capture two things. One is a batch type of optimization. First of all, in Q-learning, there's no batching, right? If you saw a Q-learning algorithm, it was just saying in the current state, take an action, get a reward, and go to the next state, and just do a equation update. Okay, that was Q-learning, vanilla Q-learning, right? But here there'll be some batching happening. That's the first feature. And the second feature is there's going to be some sort of target freezing. Okay, and these are just two phrases. We'll get to what is meant by target freezing and what is meant by batch optimization. You guys know already. It's just supervised learning with multiple training examples, like batching in neural networks. But we'll kind of understand. These two are the features which let me use function approximation in Q-learning in a reasonably stable way. Okay. So here is the deep network. In fact, it's not deep enough. I mean, it just has two convolution layers and two fully connected layers. Okay. So in particular, DQN itself has input state S, which is not a single image, but actually 4 images. Okay, 4 images concatenated next to each other. Okay, so the input is actually a tensor, which is 4 cross, in this case, 84 cross 84 in these games, and output is there are 18 joystick moves. Okay, so given that state, I need to evaluate Q of S comma A for A is equal to 1, 2, 3, 4, all the way to 18. Okay, so left, right, or top, down, jump, and all that stuff. And the reward is just a change in score for that step. Okay, so the delta between what was the score before and what was the score next. Okay, and so what I said is target freezing is the second red highlighted word, which is fixed targets, fixed Q targets, fixing Q targets, and batching. They call it experience replay. Okay, so experience replay is the name for batching, so doing some batch type of an operation. And so I'll explain both these terms so that everything is demystified. So before that, the usual loop. So you take an action A, you get a if you had a current Q function approximator already, so with some current weights. Okay, with the current weights, you take an action. Right, you can always take that action, and you get to the next state and get this delta score change, which is the reward. And what you do is now put that in a memory. Think of that as database where I got this. I was in this state. I was in this state and this action. I got to some other state and got this reward. So the 4 numbers, or actually not 4 numbers, but the 4 tuple object. I just put that in my database. Okay, so that's called replay memory. And then what you do is sample a mini batch of these 4 tuples from this replay memory. Okay, so what I'm explaining now is this experience replay aspect or batching aspect. So once I sample these observations, then I can compute the targets. Okay, so I'll tell you what the targets are, and once you compute the targets, then you can just do the batch gradient, the stochastic gradient descent update. So let me show that using equations. So this Q and so this Q represent the left hand side and the right hand side of my previous 2 slides ago, before we took the transition to deep learning and stuff like that. This was the first term, this is the second term, and we said we want to minimize the expectation of this should be 0. Remember? Now we said, okay, if expectation has to be 0, some sort of squared error of difference between these two should be minimized. Okay, as I optimize for W. But that was in a situation where these guys were fixed. I mean, these guys were known. Okay. Now I'm saying the left hand side, instead of us knowing the Q pi of S comma A, let's say the left hand side. So the first term is for some previous W values that I'll keep fixed. Okay. So W bar here is some weights. Okay, some weights, previously chosen weights or few iterations before those weights. So if I know those weights, then this first term is completely evaluated. It evaluates to some bunch of numbers. Okay, r plus gamma max of something. You can compute that because I know the weights. I know the r, s prime, and a prime. Okay, from this mini batch of samples that I got. Okay, and then I know these targets, fixed targets. All I'm asking is, can I change the w of this term here, wi? Can I change this w so as to minimize this loss function? And how do I change this w? I can just use stochastic gradient descent. Okay, so the j of w you saw before is essentially the same as this loss function, where we have somehow converted the Q-learning problem was actually there was no batching operation going on. Here we said collect a bunch of samples, collect a bunch of these four tuples, S, A, next state, and next the reward. Given those four tuples, you can collect many of them, put it in a replay memory or a database, sample some of them from that database, maybe 100 of them. Okay, from those samples you just solve a usual supervised learning problem, because if you know the samples, you can compute the right hand side and the left hand side. The right hand side has slight change, which is that I'm saying don't keep the left first terms weights as a decision variable, as a thing to be optimized. Just take the take this guy, right? So wi bar to be some fixed weights from some few rounds ago. Okay, that's all. So that's the two changes, and this is called fixed Q targets, and experience and replay is just this dynamic memory, this memory. Yeah. So those are two changes which DQN suggests. Okay, and yeah. So any questions about this part? I'll explain this again in terms of on block diagram. Okay, so first thing, there at least there's this blue this purple block, which is the environment. Okay, it has to given state and action, it has to spit out next state and reward. Okay, so next state and reward, whatever it gives us, we're going to dump it into a database. That's the green block. Okay, and from the green block we'll collect that four objects: current state, action, not current state and action, but from the database we sample object at 4 tuple. That's going to be current. That's going to be state, action, next state, and reward. Okay. 2 of those numbers, next state and reward, will go into as arguments or part of the target queue network, which is this guy. So this is the target. Okay. Remember, this is a part. The things that need to get in there are S prime and R. Okay, not A. Sorry. S prime and R are the 2 things that are input there. So those are the 2 things passed into the target queue, plus R. That's going to give us Q of S prime comma A max plus R. Okay, so that's part of the loss, minus I'm trying to find Q of S comma A comma W square loss. Okay, square loss or summation or expectation, I guess. So this is what we want to. So the DQN loss is nothing but the difference between the Q network's parameter that we want to optimize versus the target Q network. So this input over here is max plus R to the loss function, and this input over here is just the Q of S comma A comma W or theta and W, same thing. Okay, and so once you have the loss, you can take a gradient with respect to the parameter theta or W to update the Q network. Okay, so that's what we are doing here, and then you just take the action appropriately by sending the action to the environment. Okay, and it sends back the state here as well as here. Okay, so that's the DQN architecture. So what has changed? I mean, you had the original Q learning with a single equation. Now we changed by doing some batching through this green block and doing some sort of batched optimization. What is this gradient update, by saying we will have some target numbers which will compute by having previously preserved weights, wi bars that we saw in the previous equation. Using that we can compute this guy, which are the targets, and then have appropriate squared loss function where the targets are fixed. Okay, they are not being optimized. You are just optimizing the parameter for one of the term, which is q of s comma a comma w. Okay. Any questions about this diagram, or does it look too messy? Yeah. So this diagram is from their paper from I think 2014 or 15, which appeared in Nature. And here they're trying to show list games on the x-axis and performance compared to human level performance on the y-axis. Actually, I think 100% represents a professional player here. Okay, and the human level performance is like about 1/3 of it, or something like 75%. So that would be a regular human's performance, and the professional player is 100% on the y-axis. And they're showing there is a bunch of games. There's a bunch of games over here which have on which the agent, software agent, doing this Q-learning updating the parametric weights using experience replay and freeze Q targets, is able to achieve a multiplicative factor better score. Okay. And these are the games here. You can see Breakout is here, which we saw in the previous lecture, where you have to break the bricks and not drop the ball, right? Yeah.
One question.
Yeah.
So in the previous slide.
Yeah.
So in the replay memory, is it you save all the states and actions playing the whole game, or just some game? How is it?
No, I mean, it's not at the level of game. It's like so S is just a bunch of 4 screens. Okay, so we are storing S is 4 screens. The action that we took, whatever joystick action that we took, the reward, the score difference that we got, and the next bunch of 4 screens. And it's not at the level of the game, whether terminating or not. Okay, there's just a bunch of observations, what happened, in what state, what did I do, and what happened, and how much money did I get? Okay, which new state I went to, and how much money did I get? That's it. Those are the 4 numbers. Those 4 numbers are actually needed just for creating this this sort of a supervised learning objective on which you can take the gradient with respect to the parameter. That's all that's happening. So here is a example. Is this just showing for a few games? Breakout is what we discussed, and there are a few other games, and it's just showing. And this is actually good practice that you should do in your projects as well, where you kind of show the impact of doing those changes. So when there is no replay, so there's no this replay memory business, and if there is nothing like that, then you just have to do some Q-learning update as you get one data point, right? So this is the performance scores, average scores that they got. If they added this freezing of the Q targets, so there is still no replay memory, but the freezing of the Q targets. Remember, in the target function has Q of S comma A comma W minus max over A plus R. So this is the target. Okay. So given max over A, so A is not a variable. So given S comma A, I can compute this if I know W minus. Okay. So W minus is the frozen previous weights from few rounds ago, let's say 100 rounds ago, 100 minutes ago, or whatever. Okay. And so this is the target. So when they say fixed Q, that's what they mean. Under that setting, they could improve the scores by just keeping this fixed. Okay. There's the simplest version, you don't have to fix it. Okay, but then that's this version where you will not get, they didn't see high scores, fixed it, they got some scores, then they added replay. So they only added replay on the vanilla Q learning, and they got this score, and they've had both replay and fixed weights, and they got these high scores. Okay, so every new feature or every new design choice that you make here, you need to ensure that it is actually increasing the average reward or getting to a better policy. Okay, so also another point, since we are doing function approximation, we may not get to Q star at all. Okay, because if we have a simple function approximation like a linear function or something like that, it may not be really capturing the optimal Q star function at all. It's just like saying if my true curve is like quadratic, even if I search over linear function space, and that will not really fit anything, right? It will if you have data like this, which is going up like this, you can do a linear approximation, but it's not gonna get to the true values, right? So that's an issue with function approximation. And so a lot of the research here is predominantly empirical. A lot of the work here is empirical without much guarantees. Although the Q-learning, the vanilla algorithm that we have studied towards the end of last lecture and the beginning of this lecture, that has some guarantee. Okay, some very rigorous guarantee on it'll work. Okay, so let's skip the scalable version. It's just trying to ensure that it's just trying to parallelize by saying there could be multiple learners, okay, multiple Q networks or multiple it's like saying I can have multiple computers play against play Atari games, and then somehow collect all the information together and do a one gigantic gradient update and update the weights, and then again send it to all these learners, and again they'll play in a very clever fashion. Okay, and that increases. So at that time, which is I guess 4 years ago, they said, okay, on a single game, it took 14 days to get to the optimal performance. Okay, so it took 14 days in some sort of, I guess, a roughly wall clock time, and they were able to do some parallelization to get to 6 hours. Okay, so but now this is 2019, so now I think you can actually train on any of the Atari learning environments in a few hours. Okay, I mean, like on the, for example, the machines that we have. Okay, so here they have lots of machines. Okay, so you can look at the reference if you want to really discuss how much computing power they needed. Okay, so any questions about that part? Yeah.
The previous slide, previous.
Yeah.
What do you mean by fixed Q here? Are the weights not getting updated?
So that's the key point. Remember this loss function here. Okay, let me actually see. So remember what was the Q learning update? It's Q of S comma A. Let me just use lower cases. Okay, this was the Q learning. Okay, so this is the original one. We're going to update it with Q of S comma A plus alpha times the temporal difference error, which was R plus max over A of Q of S prime comma A minus Q of S comma A. Okay, this was the Q-learning equation. Okay, now, okay, there was some gamma. I think there was a gamma missing here. So there's some gamma discount number, and how do you make this? So this was the original without function approximation. Now, once we do function approximation, then Qs are not tables anymore. So you have to do something different. So you can actually there'll be weights instead. So there'll be additional weights, right? So the update is going to be something to do with weights, not Q values itself. So how do I update the weight? Remember, this is called TD error. Okay, so I'm just going to do the following. So weight at time. Okay, let me put a time t plus 1 is the previous weight minus some learning rate times some sort of a gradient. With respect to some loss function. But instead of that, I can just make it as a function of this TD error itself. Okay. No, there has to be something more. Yeah, so TD error itself, but also you need to get the gradient of Q S comma A with respect to W. So remember, the dimensionalities have to match. Remember, this was the equation. So without thinking of DQN, this would be an update equation for weights, right? So I have the new weight will be previous weight minus some gradient step, and this TD error is like if you have a squared loss, if you take the gradient, if you take the first derivative, then you drop the square, you retain the error, and this would be the gradient with respect to the function approximator. But this is actually not entirely correct, because the TD error also has this q. So actually, if you take the derivative of with respect to w of the TD error, let's say r plus gamma max over a of q of s prime a, it also has w, minus q of s comma a, it also has w. Okay, something like this. So if you take the derivative, there's this part which also has w, this part which also has w. Okay, so to get around this, what you can do is this part I want to make it not a function of w. So instead of not a function of w, so I want to make the w's fixed. Okay, so I'm going to fix these w's to some previous values w minus, which were 10 minutes ago. Okay, if the w's were 10 minutes ago, they're fixed numbers. I'm not changing them, which means that this underlying part is which is called the target is not changing. It's some bunch of numbers, r plus something else, which is can be evaluated. That's called the target, and that's fixed. Okay, that's what we mean by targets being fixed. Okay, and if you take the derivative like this guy, then you'll get a update equation which is like this: the error times the gradient of the gradient of the this guy over here. The gradient of this guy is this underlying part. Okay, so this is function approximation, but no what is it called experience replay. So here we have done the freezing. Okay, w to w minus, that's freezing, fixed. What is it called? Yeah, fixed q. So the thing fixed q just means this. Okay, fixed q just means that the targets have been fixed. Okay, and now the third part is how to make this how to make number 2 into some sort of a batch operation. Okay, by which we just mean that right now for every new for every state I took an action, I would get some new number r and s prime in addition to s comma a. I can just do this update. Okay, that will give me some performance. But what we'll do is instead of just taking the TD error times gradient of q of s comma a for the current s comma a, I'm going to pull out a bunch of observations from my replay and take an average. So there will be a summation, 1 by n summation over all s comma a from that n samples that I got from the experience replay, and then the same thing. Okay, that's called I guess experience replay or batching. Okay, so from this is the baseline. This part, the last one, the last column is the baseline. From here they are saying if I fix q, I'll get this much error. From having replay, I'll get this much error. If I have both, then I have this this much performance, and if I have both, I have the highest performance. Okay, it's like a ablation study. So you're saying you introduce a lot of tricks, but is each trick giving you some bang per buck? Okay, because simultaneously, if you introduce 10 different tricks, some of the tricks may be actually useless. Okay, if you actually just look at are they really improving any performance, they may not be really doing anything. Okay, so you need to be careful about this. And this is a very important part of, I guess, practical solutions. Is this clear? Okay. So what we'll do next is look at the second example, a case study, which is AlphaGo. There should be 2 here. So this is again now 2-3 years old, and now they're actually better, I guess, new generation are successors of AlphaGo, which are called, I guess, AlphaGo 0, and then now it's called Alpha 0, and maybe there are now newer improvements. So what changed in those improvements is basically they have simplified some of the training aspects, and they have made the system, the same architecture can be trained to play multiple games, not just Go. Same architecture can be trained to beat the top chess programs and top shogi programs and so on. Okay, so but that's fine. We'll look at the 2016 version. So how many of you know the game of Go? Board games. How many of you know chess? How to play chess? How many of you don't know any board game? Okay, you have some conceptual idea of what a board game is, right? So Go is a game. It's quite old, and it basically has 2 types of. I guess it's a 2-player game, and both players have a bunch of these stones. Okay, white stones and black stones, and there is a bunch of rules of where you can place this stone in a sequential manner given the current placement of existing stones by both players, and you care about maximizing your territory. Okay, so there's this notion of territory, and here is an example where you can the white player has conquered this much of territory, and the notion of capture just means that if these black stones are completely surrounded by white stones, then you're captured, so you will lose that territory. Okay, I mean, these are just notions, but there's a bunch of rules just like chess or other games where you can only place stones in certain locations. Okay, I mean, actually, I think the rule set is much simpler here. Anyway, and there is different sizes of these boards. So 9x9 or 19x19, which is a professional board size. Okay, and if you think in terms of states, so what is the state? State of this game is all the possible locations of black and white stones in this 19x19 grid. Okay, now it turns out that it's like a combinatorial thing, right? So I could have a black at the first location and white at the next location, and so on. And at the same time, I could have arbitrary number of stones on the board at any given point of time. So it's like for some number of stones, what are all the possible choices of what colors they are, and what are all the possible choices of where all they can be. Okay, and just sum over all the possible number of stones that can be on the board. It's a huge number, in fact 10 to the power 270 or something. So the state is too many, okay, which is the board state, and which kind of makes algorithms. So this is a completely deterministic environment. There's a bunch of rules, and the algorithms are supposed to just follow the rules and figure out what's the best thing to do next. Okay, unlike Atari, where there could be like a random Tetris. If it's Tetris, Tetris is not Atari, but like if it's breakout, then the ball can bounce. The physics of the ball you need to figure out whether it bounces properly or not, or if it's too fast or things of that nature. Here it's a completely deterministic, where to place the stone and so on. But still, it's hard for computers to figure out what's the next winning move, or what's the move which I should make so as to maximize my chances of winning. Okay, it's kind of hard. It's not, by the way, this hardness is like not a binary thing. I mean, you can create simple programs which can play somewhat well, but to really beat a human requires a lot more ingenuity, and that's what happened 3-4 years ago. Okay. In fact, this is a summary. If you only focus on RL based programs, so our lecture is about reinforcement learning. So if you look at RL based programs, these are a bunch of games, where RL programs have been shown to play pretty well. Okay, and in Go, the previous algorithms were what are called the grandmaster level, and AlphaGo is kind of has beaten that level as well. Okay, so now I think the Go programs are much more sophisticated and can beat human players. Okay, just like chess. I mean, these names you might not have heard of, but you might have heard of Stockfish or Leela chess or things of that nature. But there are games which can play really well. Chess is now humans are not at the level of computers. Okay. So anyway, this is the state of these are the bunch of games where AI agents were not the best, in the sense that they have good qualifications. Okay, there's this degree of how good a player is, but Go was just able to cross that human level performance and beat some of the top human players at that time. Any questions? Okay, so what's the problem here? So let's kind of ignore the reinforcement learning or Q learning aspect here for a moment, and just understand like what is needed to code a game to win, right? So for that, let me just talk about two things. One is if you think of the sequential decision problems, so multi-stage decision-making problems, where there's an impact of your feedback on the next state and so on. Actually, reinforcement learning is the analog of planning problems. Planning problems is a name just for the MDPs, where you know the transition dynamics and the rewards. Okay, I didn't use the word planning, but when people say planning, they say, I already know the dynamics of the environment, I already know the reward function, can you tell me what the best policy is? Okay, that's what MDP is, just a computational problem. Okay, reinforcement learning is just an analog of planning when you don't know the dynamics. Okay, now game-based problems are essentially what are called, I guess, forward search problems, which is actually just a planning problem. There is nothing, so the dynamics of the world are known. For example, in the game of Go or chess, you already know what happens if you do, if you put a stone at a bad location, they may get captured, or if you put a stone somewhere, then it's an illegal move. So you already know the dynamics in some sense, but still you're not able to compute the optimal policy. Okay, that's the central issue with game of Go and other games. Okay, so in that case, if we cannot compute even what the next move is to maximize the chances of winning, not just the next move. So what is the optimal policy? Let's forget about the optimal policy and just focus on what action to take next. Okay, so instead of thinking of finding pi of s, right, for every state what should be the best action, let me not even compute that, because maybe the number of states, as you saw, the number of states is too many. For each state I cannot remember what the action is. So let me just figure out at any given situation what's the best action to take now, and then again do some recomputation next time wherever I get to. Okay, so I'm not going to remember. I mean, I can remember what actions I took in a previous states, but I don't know pi of s, because that has to be for all states together, right? For every state you should tell me what action to take, which is kind of hard thing to compute. Okay, so what is the problem in Go? The problem is, so you want to figure out how good is the position as a state. What in this board situation, what is how good is it? Okay, so for that we'll kind of use the same terminology as reinforcement learning. So we'll say we'll have a reward which is 0 if I'm not at a terminating state, as if in the sense that I'm not won or lost yet, and RT whenever I terminate, let's say capital T number of moves, I guess joint moves, which is going to be 1 if let's say black wins, and 0 if white wins. Okay, then a policy which is going to be a policy for both the black player and the white player selects this policy. I mean, selects moves for both the players. Okay, right, because it's just a collection of two policies, and now the value function is going to be for this policy object pi in a given board situation is going to be the expected total reward, right, from that state onwards. But all the rewards up to the terminating state are all 0. Only RT is non-zero, which is actually equal to 1 or 0 depending on whether win or lose. Okay, so this is the value of that state. Value of being in a particular board state and having a certain policy is just this. It's just the probability whether black wins from starting from some state S. Okay, because RT is just binary valued, and V star of S is going to be the best thing that the black player does to maximize the value when he knows that the white player is going to minimize that value. Okay, white player is playing opposite to you, so they are going to minimize that value. So you need to figure out what to do, anticipating that the white player is going to do something opposite once you've already played. Okay, so you play first, the black player, let's say, you play first, anticipating the worst move by the white player. What is the best move you can do to maximize your value? Okay, that's what the value. So that's what's going to be. I mean, if you do the max and min, then that's going to be the optimal value of that state. Okay. Any questions about this forward search problem? Okay. So diagrammatically, what's happening is think of these white nodes as or the, I guess, non-shaded nodes as the state of the board. Okay, and these dots as the two moves, right? The black player moves and the white player moves. Okay, that gets to some other board state. Okay, maybe in that board state again black player moves and white player moves. Okay, and maybe because of that the thing terminates, somebody wins. Okay, so this diagram here is called a game tree. Okay, it's called a game tree, or I guess search tree, and for such algorithms, what they do is they want to find the best action. So in this state, let's say I'm in state ST, I want to find out what's the best action to take. Maybe I have two actions, okay, two actions, two combined joint actions. Just think of those two actions, two paths that lead me to various things. Which action should I take? Then I just need to look ahead, right? I need to like, okay, if I take this action, what will happen? What will happen? What will happen? And that's kind of diagrammatically represented here in terms of a game tree, okay. And what we need to do is just find from this starting state what is the best action to take. So from this starting state I have two possibilities. I'll kind of explore as in I'll branch out, go down each path in this tree from this root all the way down, and figure out like what's the in which let's say maybe the first move, this is the first move, and this is the second move. In each of the moves, whether the first move led me to more wins or the second move led me to more wins. Okay, whichever led me to more wins, that's the action that I take. And this answers the question of figuring out what to do now, and forget about solving the whole MDP. Okay, forget about solving for the pi of s for all the states together. Okay, and so it turns out that for games this branching factor, okay, the number of because there are 18 joystick moves, and so the number of actions could be too many. Okay, so then there will be too many states, and so on. So there's a combinatorial explosion in the number of paths that you need to take to figure out which action is better. Okay, so instead of going down every branch and figuring out whether I end up in a winning situation or a losing situation, you can do sampling, which is just that you just try one random action, appropriately chosen random action, then get to some state, try some other action, try to get some state. So instead of looking at all the branches, maybe you try out few paths. Okay, maybe out of the 20 paths, I try out 10 paths arbitrarily chosen, and maybe these 10 paths give me some partial information of which move is better, and I'll take that move. Okay, and that's called simulation, basically just trying out a few paths. Okay, yeah, and then assess the quality of the two actions that you can take, the two black circles that we have. Okay, and so that just represented in terms of a bunch of notation is just this. So you're at a current state ST. You can simulate capital K paths. So from that ST, you can take some action, go to next state, take some action, go to next state, all the way to some terminal state where you got some reward, and you can do it K times. Okay, and then because now you know what all what all paths led to a positive, what all paths from the current state, if I took some action, led to rewards, and what all paths did not get to rewards, you can actually figure out what is the value of taking the best action in that state. Okay, remember, value of a state is just the expected total reward you can get from that state onwards. So with these K simulations or K paths, you can say what is the expected value of me being in a certain state, or expected value of me being in a certain state and taking a certain action. Okay, this is just the average of these samples. Okay, and in fact, let me explain it through two specific, diagrammatic approaches. One is Monte Carlo search, and the second one is Monte Carlo tree search. So, what is Monte Carlo search? Okay, so by the way, so how am I getting these actions, rewards, next states? Let's assume there's some model or a simulator which will, or a rule engine like for chess or Go, which will tell me what the next state is and whether I won or lost. Okay, so what is simple Monte Carlo search? It's like it's a situation where what we do is so from a I'm in a state. I want to figure out what is the best action to take in that state. Okay, let's call it the current real state, because I want to figure out what's the best action that I can do for this guy. But I have access to another simulator, okay, where I can figure out, okay, if I take this action, what happens in the next state? What happens if I take some other action? What happens in the next state, and so on. That's going to be the sequence. So in this current state, I took some action, and all this is going to be for a specific action. I want to figure out what all would happen. That will be given by this model MV, okay. And then the quality or the state and state action value for that state would be just the average of the rewards that I got. Okay, this we have seen, the average of the total returns from that state onwards. Okay, and once you know the value of the state, you can just pick the argmax, whichever action was the best, and that's your action for the current state, and then you repeat it at a new state. Okay, so you do this operation for every time you are in a some state ST. So you're in some situation, board situation, just do some Monte Carlo runs, get some estimate of the total returns, and figure out which action is the best. That's the simplest thing you can do, and that's written in algorithm format here. Okay. Any questions about simple Monte Carlo search? No questions? Is everybody following what I'm saying? Okay. Okay, so pictorially this is what it is. So if you have board state, let's say I choose 4 simulations. So from that board state, I keep querying the engine of, okay, if I do this, what will happen? If I do that, what will happen? Okay, and it will say, okay, if you took if you took whatever, if you took okay, here there's a simulation policy as well. If I follow according to a particular policy, then these are the outcomes. Eventually I'll win a couple of times, lose a couple of times. Then the value of that state is just number of times I won divided by number of Monte Carlo runs I did. Okay, so that's the value of that state. It's just a Monte Carlo average of a bunch of numbers. Okay, I forward simulate what all can happen if I take a certain action, and sometimes I win, sometimes I lose. Then that's the value of the state. Number of times I win divided by total number of times I simulated. Okay. And so what we're going to do is, so that's simple Monte Carlo search. So you need to understand what simple Monte Carlo search is so that we can get to Monte Carlo tree search. So actually, let's take a break here. I see a lot of people are exhausted. So let's take a break and resume at 7:30 or 7:32 maybe.